So hello everyone, this is Akshay here, and as we discussed in the previous video, today we're going to discuss the use case of a topological sort, that is the shortest path in the directed acyclic graph. Now, this question can be solved via three approaches. It can be solved via topological sort, via Dijkstra algorithm, and via the Bellman-Ford algorithm as well. But since I have not discussed the Dijkstra and Bellman-Ford in my playlist, so we will cover this question again once we have done the Dijkstra and Bellman-Ford, right? But let me give a very small game. So Dijkstra algorithms only work for the positive weight. It does not work for the negative weight cycles. That is why a new algorithm was introduced. That is the Bellman-Ford. It handles the negative weight cycle as well, right? Negative weighted graph as well. So now, getting shifted to our motive again, that we will be solving this question using the topological sort, right? So there are two cases I need to discuss. The first one is the shortest path, and second one is cycle exists. So our next video will be on the cycle exists. So before moving ahead, if you're new to this channel, please like, share, and subscribe, and hit the bell icon to get the regular updates. Let us proceed ahead with today's agenda. Great. If you have seen my previous video, I have told you, I have explained you that how a topological sort can be done using the DFS based approach. This was a dry and I showed you, but let me give you a very quick glimpse. If you have not seen the previous video, it will just help you. It will just take 1 minute. So let's say this is the graph 0, 1, 2, and 3, 4, and we have marked the indicative vertex with the red color, right? And we are actually what we are doing is that we are calling a DFS function for each and for the vertices starting from 0 to the way to the D4, right? So it is coming for I equals to 0 to I less than equals to 4 I plus plus, right? So dfs of 0 will give call to its neighbor, that is dfs of 1, and then 1 will give call to its neighbor, that is 3, and 3 will give call to the neighbor 4. Now 4 has none of the neighbors left, right? So what we will do, that we will push, whenever the recursive call is over, we will push that particular element in a stack, right? And we will push the attack 4, then we'll push 3, 1, and 0, right? Now since this was the call for I equals to 0, now for I equals to 1 I will call, and I will see that the 1 is already visited in the recursive call we made for the 0, right? So I will just skip it. I equals to 2, I will just mark it again. I will for I equals to 2 I can see that it is false. Then I will make a recursive call for dfs of 2, and I can see that none of the neighbors of the 2 are not visited, right? 3 and 4 are already visited, right? We have marked this in this array, correct? So we will end this recursive call here, and we will push this 2 into our stack. Now for 3 and 4 again it's already visited, so we do not make to recursive call there. So now this is your stack, and this is actually your topological sort, right? If you just pop out the elements from this stack, you will get 2, 0, 1, 3, 4, and the topological sort for this particular graph you can verify manually is this answer, right? So multiple answers can be there for topological sort, because at one particular iteration you can get two answers, right? How we can do a topological sort? So whenever the node has the value in degree equals to 0, we print it. So in this particular graph we can see that 0 and 2 both have the value in degree 0 at the starting point, right? So either we can say 0, 2 or 2, 0, right? And that is why the reason we say that the topological sort may have more than one answer, right? I hope we are clear to this point. Now if you have seen my previous video, you should have directly jumped here. I will mention that thing and in the description as well. And if you want a more in-depth explanation, please visit my previous video. I cannot spare more time on it. Okay, let us move back. Let us start for our use case, the shortest path in the directed acyclic graph. Okay, so that's the algorithm I have written here. What we need to make changes is that we need to initialize a distance array, and initially all the values should be marked as infinity because we don't know the answer, right? But the source node, let's say this is the source node, right? So the source node, the distance would be 0 because I want source to each and every vertices, right? Each and every vertices, but the distance from source to source would be 0, right? So that is why I'm saying distance of source is 0. Then the third step is to find the topological sort of the graph, and for every adjacent v of u. Now this v of u is nothing but for every neighbors of u, you need to check that if distance of that particular neighbor of u, that is represented by v, if distance of v is greater than distance of u plus weight value of u to v, right, then you need to update it. You need to update it with the minimum one, right? Let us do a very quick dry run so that we can understand more in depth that how it is working. Let us take the same graph example I have shown you. So if I just tell you to, before running the algorithm, can you find me the minimum or let's say the shortest distance from 0, this is the source, to each and every graph, and this is the weight given here in blue color, right? So 0 to 0 you will directly say it's 0, right? But for 0 to 1, the shortest distance is that you can move from 0 to 1 in this using this weight 1, so it would be 1, right? 0 to 2 you can say 1 plus 2, this 1 and 2 would be part of your path, right? And you can say that the answer would be 0 to 3, the answer would be 3 again, right? For 0 to 2 you can see that there are no edges, there is no path possible to reach from 0 to 2. If you can come 0 to 1, you can go from 1 to 3, but from 3 you cannot go to 2, right? You can go to 4, but 4 cannot move to 2, right? So that is why if there is no path possible, you need to return -1 for that case. For 0 to 4, you can clearly say you can come from 0 to 1. So 1 plus 2 this one, and plus 2 this one, right? 4. Correct. So 2 plus 2 plus 1, that's 5. So that's the answer. So how we can do this? So whatever I just told you in the pseudocode, let us do that, right? If you do a topological sort for this particular node, or for this particular graph, so what would be the value in the stack? Now again, pause this video. If you have understood my previous video of how we can do the DFS based algorithm, then you must have understood how to fill this stack, right? Please fill this stack, and then I will show you what the other iterations are. So great. तो ये वही होगा यार जो अभी हमने ऊपर डिस्कस किया था, तो वहां से उठा लेते हैं इसे. So it would be 4 3 1 0 2 because it was the same graph. Great. So it was 4 3 1 0 2. What I need to do is that I will pop out first element and I will check the 2 का neighbors कौन से है, right? The neighbors of 2 are 3 and 4, right? So I will see that if this distance of u, if it is already pointing to infinity or not, right? So I will have my distance array, right, for 0 1 2 3 and 4, and I will mark this as 0 and this as infinity, infinity and infinity, right? So distance of this 2 is already pointing to infinity, so we cannot compare it, right? Like अगर मैं लिखूं यहाँ पे distance of 3, मैं किसे चेक कर रहा था? Distance of 2 plus the weighted edge of 2 to 3, right? So distance of 3 is already pointing to infinity, distance of 2 is already pointing to infinity, and 2 to 3 is nothing but 4, right? So there is no sense to make the comparison, right? So there will be one more if statement, that if this particular value, whatever the value you have pulled it from the stack, if that particular value is having distance equals to infinity, you need to check, right? Right. So I will just, let's say, I will just say here, if distance of u is not equals to infinity, then only you need to check, right? Please don't mind my handwriting. It is just written if distance of u not equals to infinity, right? Many of you I can see in the comment section advise me to to better my handwriting, but यार समझाने से ऐसा हो जाता है, ठीक है? So please follow along. ठीक है. Okay, so we will pull out the next node until unless our stack is empty. For 0, let me change the color here. For 0, the neighbors are 1, right? So I will just say that distance of 1, I will just compare it with the distance of 0 plus the weighted value of 0 to 1, that is nothing but 1. Distance of 1, if you see, that is infinity, right? So this is infinity. Distance of 0, if you see, it is 0. So it would be 0, and distance from 0 to 1, is it? Yeah, 0 to 1. What's the value from 0 to 1? It's 1, right? So infinity greater than 1, definitely, right? So we need to update it with the value 1. Distance of 1 would be updated as 1, and if you can see, that was the answer as well. We are getting closer to the answer. Great. Great. Now let us pull out the next node because all the neighbors of this 0 has been processed. So we will pull out this 1. What's the neighbors of 1? Only there is one neighbor, poor 1. There is 3. So I will just say distance of 3. I will compare again that distance of 1 plus the weighted value from 1 to 3, correct? Okay, so the weighted value from 1 to 3, distance of 3 is what? Infinity. Again, there is a need of comparison. So distance of 1 we have already updated, so it would be 1 plus weight of 1 to 3, it is 3. So infinity greater than 4, definitely. So we will update d3 as 4. So I will update it as 4. Again, let us move the next element, that is 3. So the neighbors of 3 is just 4, I guess. Yes, only 4. So I will again compare that d of 4, is it greater than d of 3 plus weight of 3 to 4, right? So if you see that the d of 3 is nothing but pointing to 4 plus weight of 3 to 4, what's the value? 2. So, and d of 4 was pointing to infinity. Definitely infinity is greater than 6, so let's update it with 6. 6 or 5? Let me check again. d of 3 is nothing but 4. Is it? Weight of 1 2 3. Okay, so 1 to 3 it was 2, right? So this would be 2, not 3. So 1 plus 2 will give you 3. So this is not 4, this is actually 3. And this 3, d of 3, so we have taken it 3, so it was wrong. This is 3 plus 2 5, right? So it would be updated to 5. So there was just a slight mathematical calculation. Okay, so and now you can see that that's the exact answer. For if you can just match it, if you can just tally it 0 to 0, 1 to 1, 3 to 3, 5 to 5. But here it is infinity and I'm getting -1. The question says that if you do not find a path, replace it with -1. So what I will do, I will just run an extra loop and I will just iterate a linear search, and whenever I'll get an infinity, I will just replace it with -1. As simple as that. Let us now look at the code. Again, I'm saying if you're not interested to run, and please pause this video here and try to dry run this test case by yourself. Even I encourage you even more to take a test case from the problem. I will mention the link of the problem in the description. Please take some a graph here, right, and try to dry run it. So let us see how the input and output is given. So it is saying in this 0, 1 and 2, it is saying that there is an edge from 0 to 1 and a weight is 2. For 0 to 1, it is saying that there is an edge from 0 to 2 and the weight is 1. So first of all, we need to make an adjacency list, right? How we can make that adjacency list? So the structure I want here is, हमारे पास structure दे रखा है इस तरह का 0, 1, 2, right? And then 0, 2 and 1, right? And this is nothing but this is indicating a node 0 which is pointing to 1 having the weight 2. Now for this, there is a node 0 which is pointing to 2 having the weight 1. Right? That's the graph. I need an adjacency list. I need an adjacency list which will have this vertical values will actually represent the node values, right? And I want here the neighbors. A list of pair, right? 0 has relation with node with what weighted value? 2. So it should be here. 0 has a neighbor to 2 but with what weighted value? 1, right? So I want this particular data structure, right? So that it would be easy for us to write a code, right? So first of all, what we need to make for this thing, we need to make a class node, let's say class node, which will accept 2 parameter u and v, right? Which will represent 2 parameters u and v, and then we need to make a 2D array list, which will look like this: list node, and then list again, and we will make this name as ADJ. That is it. That was the prerequisites I needed to give you. Please pause this video here and try to code this approach by yourself in the code editor, and I will just give you a walkthrough now. Okay, so that's the node class I was just saying about you, that it will have 2 parameters, that is v and w. V is nothing but the destination node, and that is the edges directed towards it. That is the destination node, and no, not the destination node, that the edge is directed towards it. That is from 0 to 1, then this is the 1, right? And the weight associated from the node towards v, right? Great. Now, okay, so as I told you, this would be let's say that our adjacency list, and for each and every entry we need a horizontal list as well, right? So in Java you need to declare it. You need to make an actual physical list by using a for loop here in the memory, right? Then again, using this 2D edges array, I'm just now making my custom adjacency list so that I can write an easy code, right? So that's what I'm doing. That for each and every it is saying 0, 1, 2, right? So for the first value, I'm getting to using this first value to access the index of our EDJ, right? And then 1 and 2 would be acting as a pair in the horizontal list for that particular index, for this particular index 0. Great. I hope I hope I'm able to make sense, and you are able to imagine it, right? I've already shown in the dry run. You can also move back to visualize that how this thing is running, right? Okay, so we have a Boolean visit array. Again, visit array is must because we do not want to visit our node twice. We needed a stack. So from here on onwards, we have written a standard topological sort code of the DFS based manner, right? So stack, why the Boolean array is there, what is this for loop is doing, and yes, all these codes, that is from line 58 to 66, and this DFS function, what these are all doing are part of the topological sort. I will not explain you. I have explained you multiple times, right? Please, I have explained in the starting of this video also for the 2 minutes, and if you're not still understood, then please watch my previous video, because that's purely based on how to do a topological sort using a DFS based manner, correct? Let's get started with the rest of our codes. So we needed to make, this was the step 1, we needed to make a distance array, and we mark it every entry as infinity, because we as of now we do not know what would be the distance, and we need to compare it, right? So, and mark the first the source distance as 0, because from source to source the distance would be 0. That makes sense. That makes sense completely. Yeah. Now we have a while loop, and this stack is actually containing the order of the topological sort you have, right? The order of the elements responsible for the topological sort. I already showed you the dry run. We keep on popping out the elements from the stack, and we keep on checking if it's not equals to integer.max value. I have already explained you why we are checking it here. I've showed in the dry run. Please revert back and see it. Let's not waste the time to explain the same thing again. Now we have a for loop, right? For this particular u, I need to iterate in its neighbor, right? And the neighbor is present where? In the horizontal list, in this list, right? I'll just in this horizontal list, right? In this horizontal list, and the type of this list is what? the value or let's say the entries of the type of this is what, a node, right? So that is why in this for loop I have written node current, and let's traverse back into that horizontal list. I'm just checking now. If distance of current dot v greater than the distance of u plus current, thus the weighted is from u to v. If it is greater, then you update it with the minimum value, right? And you keep on doing it until you have relaxed, or let's say processed all the neighbors for that particular u, and until you have popped all the elements from the stack as well, right? And there's the for loop extra I've explained to you, that if the particular distance is pointing to infinity, then this question is asking return -1 for that vertex. So that is why we have marked this as -1, and last we are doing the distance array. I hope that you were able to come at this point of this video and you have a very good understanding on how the topological sort and the use cases has been served here, right? I definitely hope, and I genuinely hope, that you have got a very good grasp, a very good logic for this particular problem. And yes, it's a very free channel for you guys. I have made I have made a free channel for you guys. So there's one more thing free for you, that you can hit my subscribe button, and I can get motivated to continue this playlist, right, covering all the topics. So yes, till then, let us see the C++ code as well. So, and what would be the time complexity for this code? Since we are using a basic standard topological sort, so it would be O of V plus C, and V plus C is nothing but, V is here the vertices, M is nothing but the edges, right? So it would be M plus M, and again O of V as the space complexity, because you have Boolean visited array and the stack array. So V is nothing but here is N, right? I have replaced also N with V. So that is why O of N here. And that's it. Let us hit the submit button. We'll do the C++ code now, and we will end this video as soon as possible. So great, my streak is also done, and we have done this question. Let us move to the C++ code. Again, you can access this all the code in my DSA repository. I will mention the link in the description as well. Okay, so that's the C++ code. That's the same code I've explained in Java. We have made a class node that can accept two parameters, that is the v and w, and then we have a shortest path. Starting the topological sort from here, making this particular thing as an adjacency list, just to write an easy code. Then topological sorting starts from here, and then we have a distance array. We did the same thing, that the popping the elements from the stack and then comparing it with the distance. The same logic I have showed you in the I have explained you in Java, right? And that's it. Let me just scroll it back. Yep. And you can see all the test cases have been passed successfully for the C++ code as well. Now let us end this video here with a good note, and let us meet again in the next question. That is, if the cycle, can we check the cycle existence of cycle using topological sort? And then we'll cover the further algorithms, that is Dijkstra, the Bellman-Ford, and others, right? So yes, let us end this video here. Till then, keep learning, keep going. Bye bye, and take care, guys. Meet you in the next video.